That would be 100 or so students, and that's, remember a couple of weeks ago we talked about the nuclear physics stuff, the gamma sphere. Those are experiments on a totally different scale where we had maybe 12 people, 5 to 12 scientists working on it. And that would cover an experiment with 1 week instead of a year. The analysis is 3 months instead of 4 years. And then you repeat it again. You need several of those experiments to get updated to do something. So those are the different scales of nuclear and particle physics.
Josh?
Yep.
I don't quite understand the reason for having magnets in there. Because these forces, are they all affected by magnetism, or does it depend on how they're charged? Or
It depends on which particle. Some of the particles are affected by magnetism if they have a charge.
right?
And the more charge, the more the effect is. And if there's less charge, if there's no charge, they're not affected at all.
Not affected.
Right. The other thing is that the momentum, if I am affected, how much I'm going to curve.
Mhm.
How much I curve. First of all, which direction I curve is whether I'm positively charged or negatively charged. How tight the curve is my momentum compared to my charge. So that charge to momentum ratio. Most of these things have very simple charges, charge of a small number. So I can tell a lot about how heavy it is, basically, just on how far it's curving.
I'm going to ask you a really silly but obvious question. When you design these things, how do you know they're going to work? The machines themselves,
Right.
Separate everything.
That's why there's a progression, an evolution in these machines, from things that started very simply to things that get more and more complicated. There's really two almost totally independent sides. One is the accelerator, how do I make the protons and antiprotons, how do I put them in a ring, and that accelerator physics is its own world. It's almost entirely divorced from the world of particle physics. Particle physics does get deeply involved in the design of the detectors. And what makes it possible to make these detectors like this and sort out what's going on is knowing the different properties of the different particles. So one question that comes up a lot is, what's the practical application for all this particle physics stuff? The answer is, well, physicists really don't like practical applications. And that's why on that chart that I showed in the first couple of days of the practical versus the sexy, we're on the sexy end here. And although this is as sexy as you get, it can still do experiments. There's the string theory stuff where we just kind of go off into philosophy or whatever we're doing. But certainly not experimental physics anymore. So the real application of knowing all this is that I can build a detector to be able to know more of this. So it's been that bootstrapping procedure. And so we had a couple of weeks ago, we had the whole zoo of particles. We didn't know what was going on. We had these things behaving strangely. We assigned them a property of strangeness. That was all to map this out. And once we had this mapped out, then we can go on and figure out what these other particles are, make predictions based on this, and then build a detector and say, okay, now I want to build a detector. If I want to find my muons and sort them out from the electrons, now I know how to do it once I have these pictures. So I know their mass, I know their charge, I know they don't feel the strong force, I know how to sort them out. I know I can build my sieve. And that's really what the application for this is. And that's why it took a while to get to these complicated collision detectors now, whereas originally we talked about last week, the bubble chambers, where I just have to watch the paths of the particles and just see what I can see looking at everything.
Okay. I was doing a question. Who manufactured this kind of stuff? Is it General Electric or?
No, these are hand-built.
What I'm saying, there are not many colliders in the world.
Right.
As you find a very small number of them. If you manufacture for only those, it must be extremely expensive to create. Well, the individual pieces are taken, so to speak, from mass production pieces.
They would be expensive. They would be much more expensive, except grad students work very cheaply. These are not cheap machines. The big accelerator that they were building in Texas was supposed to be $8 billion. When it got to about $12 billion, Congress shut it down, and we abandoned that, and then the biggest one became the one they built in CERN. We were $8 billion in. By comparison, these things are so expensive that was the price of per aircraft of the first set of B-2 bombers, were $8 to $12 billion a piece. So this is it's like the cost of one airplane. It's really expensive. Fancy airplane still. A lot of the stuff, there's certain specialized components, the superconducting magnets that you need to build the accelerator. There are companies that specialize in that. If I'm building, they're not mass produced in that sense, but if I have a ring that is a couple of miles long, and I need to build 2 miles worth of magnets, that's a lot of magnets, so that's worth it for a company to come up and do. On the experiments themselves, the detectors, those are designed, there are people that really get into this, who have spent their careers on this. There are, and a lot of these people are physicists or mechanical engineers that are working in physics departments to help figure out how to do it. A lot of the construction, there are things where we'll send them out to a company, build me a couple of these, the prototype shops that will do that. A lot of the work, though, is just done by physicists and grad students. A good example is stringing up wire chambers. Yesterday there was the detector where I can, last week, it tracks how the particle passes by going through a set of screens of wires. All those wires have to be strong. So if you talk to old grad students, it's all, hours and hours spent pulling strings tight and tying them off and getting the tension right one after the other repetitively for the first 2 years. And that's the first 2 years of what you do, and then you go to one of these experiments, and you sit with the experiment for 2 years, and then you go and do the data analysis. That's why theorists graduate much more quickly on average than experimentalists.
So like these experiments, I mean, to the untrained eye, like if I were to go, would it just be like, oh, nothing happened, but people are very excited about data, and like would it be, oh no, look, there wasn't a particle, and now there's a little.
No, what you'll see is if you get into the collision hall, you'll see something that looks either like that, or you'll see, there's the picture there, looks like this. This is a KTEV, the fixed target experiment. And you can walk up and down here. There'll be the hum of all the fans. Mostly what you see
Not while it's running.
yeah, but right. Mostly what you see is vacuum pumps. That's because these things have to be in vacuum, and the pumps probably make the most noise and take the most maintenance. That's kind of the dominant experience. If you're there while it's running, you'll be in the control room, which looks like a room full of computers. Depending on the scale of the thing, you're almost never in the control room for the accelerator itself. That's kind of specialist technicians. But the control room for the experiment is just the computers that are collecting it. And really all you're seeing is the stuff that's monitoring the experiment, making sure nothing is broken or dying in some way. The data is really just being written to, I don't know what they do now, written to magnetic tape, at least when we were active in the field. And then all that is analyzed later. So there's no excitement to see when you're there. And even the discovery of the top quark and the Higgs for that matter, that's all done offline. Right in the control room and there we saw it. It's, you look at the data continuously, it's separate from the labs when you see things. Okay, so what we've been talking about so far, this is the world of mechanics. Classical mechanics is where we live. This is billiard balls, driving a car into a telephone pole, watching the apple fall, the motion of the planets, for the most part. The motion of the planets you can see in your backyard with a telescope. That's all classical mechanics stuff. Everything you think of as high school physics or college physics for that matter. But I can do two things. I can get smaller and get faster. If I get smaller, that's what we've been talking about. Quantum mechanics is a different set of rules that applies when things get very small. These rules all have to be able to move back and forth with something called the correspondence principle, that if I go at the boundary between these things, they have to smoothly account for each other's behavior in order to be accurate theories. It's not just that I cross some threshold and all of a sudden all the rules are different. There's got to be some kind of a way I get from one to the other. But essentially, everything we've been talking about is in quantum mechanics. And I've shied away from getting into the details of that. You can see why, because as weird as whatever we're talking about, or as hypothetical as it seems, it gets far more strange, not strange with an S, but weird when you get into quantum mechanics. Relativity is weird in its own way, or at least anti-intuitive. And that's what happens when things get really fast. So the rules of quantum mechanics account for some of the stuff that I've said that doesn't necessarily sound like it makes any sense. And relativity, we haven't talked that much about yet. We'll talk about it a little bit at the end today. But that's the Einstein relativity. That's basically has to do with things that are moving quickly. In both cases, there are things that we have to account for in order for most of our modern technology to be able to work. We can't do any kind of modern technology with just classical mechanics. It doesn't account for the effects that are there. If I go small and fast, I get to quantum field theory. And that's something that I have not figured out how to convey without math that is really close to the edge of what I can do, for that matter. So we're not really going to get into quantum field theory, but that's where you go small and fast. And it's fun, but it's not straightforward. Okay. That'll come at the end when we get to the relativity stuff. So what I want to talk about a little bit is quantum mechanics. Quantum mechanics, mechanics itself, like the basic physics, the billiard ball physics, is where is something at a certain time? What happened? You know, how do I find a particle? Two things bang into each other, balls bang into each other. Where do they go? What happens? Quantum mechanics is how we do that with very small things. The key thing with quantum mechanics, the core element of quantum mechanics, is the wave function. I don't have a place that something is. I have a probability of where I might find it. So if I say, where is this thing? This thing is somewhere in this area. So this is where I am. I can't say my particle is here. My particle has a probability of being here, most likely. It's a little less likely that I'll find it here. And it's very unlikely that I'm going to find it out here. And it may be impossible to find it out here if this probability really goes to zero at the end. So for any system that I have with a particle, I can't tell you where that particle is. But what I can tell you is how likely I am to find it somewhere. That's until I try to find it, until I actually measure where it is. If I do something, like shoot something in here and say, okay, where are you? Take a snapshot of it somehow. Then it's going to be somewhere. I'm going to see it. So it might be here. Or it might be over here. And then I don't have this probability anymore. I have my particle. It's right where I said it was. If I turn my back and then I go back, it's still going to be there. Because that's where it was. That's where it actually is at this point. Before I measure it, though, it's not there. I just have this probability. I know it's somewhere in that area, and I know how likely I am to find it at each point along this line, but I don't know where it is. And the point that's hard to understand, where people tend to jump, and this is including physicists around the development of this stuff, includes Einstein until the day of his death. The belief, the thing that's hard to understand, is that it's not that I don't know where it is. That's not the correct statement. It's that it is not in a particular place. So Einstein's belief was that the particle is somewhere, you just don't know where. But the reality is, the particle is not somewhere. It is equally, it's distributed with a certain probability over this entire area. And as soon as I look at it, that's when it becomes in a particular spot. And that's why if I look away and look back, it's still going to be there. But it's not there until I look at it.
Is the probability always a bell curve?
It is not. It could be anything. For the systems that we tend to start with, we do, instead of doing a bell curve, we use a sine wave. And the reason we use a sine wave, which is that even wiggle, is because out of sine waves, I can build any shape of any kind I want by adding them together if they're at different frequencies. So that's the basic thing we start with.
Isn't this what we call observer dependence?
It is, and we'll get to that. The question is then, what is an observer or what is a measurement? It's not the observation. We tend to get into a philosophical thing. Well, if I saw it, that's what made it happen. It's not that. It's a more physical thing that happens. And we'll talk about the cat in a few minutes, and we'll answer that precisely. Jane?
Why can't the particle move? Like, once you identify where it is.
Right. So that's the key thing that happens. Is this is my wave function. That's what it's called. The description of the probability of where the particle is. Once I do my measurement, we say the wave function collapses, and I don't have the wave function anymore. Quantum mechanics essentially stops doing its thing, and the particle is just there. The wave function has collapsed. Now it's in a well-defined place once I've done that measurement. Because I've forced it to make a choice. And once I force it to make a choice, that choice is made, and that's been done. Now the particle could still be moving. It could be, bouncing around, maybe it's in a field of flying, it could be doing anything. But that probability has collapsed. There's no longer any probability of finding it anywhere else. It is where it is. I forced it to choose.
But where it is means in relation to something. I mean, it has to be,
Yeah, so
maybe other part of the other volume or other whatever.
could be The answer is basically yes, it has to be in relation to something, but I can define whatever something, this applies no matter what kind of something I have. If I have a particle in free space, it's a little more complicated. I have, instead of a wave function, I have a wave packet, and that's when you get to the particle wave. The particle's a wave, the wave's a particle, and that's because I have a packet of this probability that's kind of the whole packet that's flying around. But in the simple cases we talk about, we construct some kind of a system where it is confined. Yeah.
My question was, when you say, only when I look at it, I know where it is.
Right.
Okay? So if I look a week later, will it still be there? Or could it have moved? But basically it's in the same area or something? Like that's what I mean with
Right.
to something, relationship to something. Okay? It cannot be
So there's-
somewhere totally out of the stratosphere or something.
There's two different things we're talking about. One is where the particle is in terms of is it moving somewhere? Okay, particle motion. And that applies in the sort of same classical mechanical picture that you're used to. If it's moving this way, I can watch it here, it's going at a certain speed, I know where it's going to be later and later and later. That's the motion of the particle. What's happening in the wave function, the particle is not really bouncing around in here, and I just don't know where it happens to be. The particle is smeared out over this entire area. It's not actually moving around within this curve, within this probability. It's just one smush of an idea of a particle, and then all that smush collapses down into a particular location when I do that measurement. I don't know what that location is. I can't choose it. There's nothing I can do except to basically interrogate it, to ask it, where are you? And then it says, oh, okay, I'm here. It'll pick some place to collapse down into. Now, so the important thing is it's not that I can't tell where it is. It's not that I can't predict where it is. It's not that it was somewhere right before I measured and I just didn't know where. It just isn't anywhere specific. It is smeared out over this entire area, and it's forced to only become in a place when I do that measurement. This is different. This is not chaos. This is not the chaos with a capital C, right? This is not the sort of inability to predict weather because I don't have enough information. It's not that I don't have enough information. It's the information doesn't exist. There's nothing, there's no property, there's nothing I can do. There's no perfect understanding of the universe knows where this is. It doesn't exist in a particular place. It's not that I don't know where it exists. That's a key thing.
To choose where it's going to be?
You can't choose where it's going to be. You know within, you can set something up that changes the shape of what the probability is, but you can't choose where within that probability it's going to be. And that's the key, that's the fundamental core concept of quantum mechanics. Now, as I said, Einstein never accepted that. He accepted that the math of quantum mechanics worked. But the idea that the particle was really smeared out and it didn't have a place, there wasn't what he called a hidden variable. So there must be some kind of a hidden variable. There must be something that we just don't know about. And it turns out that it's clearly proven that does not, it's not true, that's not the right picture, that it really is just smeared out. Now in terms of understanding this conceptually or intuitively, you can't. You won't. There's people like Feynman, all the famous physicists have some kind of a quote about either if you think you understand quantum mechanics, or anyone who says they understand quantum mechanics clearly doesn't, or that it's impossible to know, or no one understands quantum mechanics. What they mean by that is not that no one understands how to do it. Any practicing physicist knows how to do quantum mechanics. You have to be able to do your job. But you don't understand what it means. So that search for the meaning of it, which has led certain people off in a crazy direction, or more mystical direction in some cases, that's not really what we're talking about.
So the difference between the classical mechanics and the quantum mechanics is not just the small size of the particles, but it's the conceptual things that the billiard ball, you know where it is? Unless you're talking that also has a space that we don't know.
Right, so these, quantum mechanics, it's the rules that apply when something is very, very small. When something is big, all those rules actually still apply. The big balls, if I have a baseball, it also does this. But the size of this probability curve is so tiny that there's no measurement you're going to be able to do that will detect it. You can only start detecting this. This only gets big when your particle starts getting really small. So that's that correspondence between where quantum mechanics flows into classical mechanics. If I take the laws of quantum mechanics, and I start making particles bigger and bigger and bigger, I am back with Newton, and everything works the way you expect it to, just because of that size. And so there's certain, what look like magical things that happen in quantum mechanics. They would happen with a baseball, throwing a baseball against the wall. But it would take several times or several million times the lifetime of the universe for it to happen. So the probability of finding it somewhere else is 1 in 5 zillion times the lifetime of the universe. That's what we mean when we say never. It's less than one chance, 1 in 10 lifetimes of the universe.
Have scientists found those crossover particles that are like big enough to have both characteristics?
Yeah, and that's, as we go from quarks to protons to neutrons and get to an atom, we do have all these characteristics. You can describe things in both ways. And there's approximations that you can make that apply in one case, and you don't get exactly the right answer, but you're close enough with classical mechanics. And if you want to figure out why it deviates from what classical mechanics tells you, the quantum mechanics gives you the answer to that. So that's where you see the overlap.
Remind me again, who was the physicist who developed this theory?
Unlike, something like relativity is easy. It's credited to Einstein. There are a couple of other people, Poincaré, that worked on it. Quantum mechanics is a team effort. And really several people were involved in getting bits and pieces, and it came very chaotically and out of order. When you study it now, you can go back and learn things in a way that makes sense. But it took a while because things didn't necessarily make sense.
Who were they?
Their names?
Who were, yeah,
Well, Heisenberg, Bohr. Yeah, there's a long. All the first half of the 20th century physicists were really involved. So the way to what consequence of this is this was just an arbitrary function, but if I take a system, by which I mean I'm going to make a well. It's called an infinite well. I'm going to build a wall. It's got a floor, and I have another wall on the other side. And this wall is infinitely high, goes up forever. I'm going to take an electron, I'm going to stick an electron in this bucket, in this well. If this goes infinitely high, the electron can't get out, no matter what, even with crazy quantum mechanics rules, because there's no place for it to go. That means the probability of being outside is 0. So I have a probability in here, that's my wave function, and I can't be outside. This thing is it's called the infinite well potential. It's the basic problem of when you start out quantum mechanics. So the simplest thing I can do is this. This is my probability function. I can do all those measurements I was talking about. I can collapse the wave function. I can tell you where it is. If I add more energy to this electron, this is the least energy it can possibly have. This is also why I can't get to absolute 0 in temperature, because temperature is something moving. I can't make the thing stop, because if I could make it stop, get to absolute 0, I can tell you where it was. I can tell you where it is. I can't do that. I'm in quantum mechanics. I can't pin it down. It's got to have this wave function somewhere. So I can't get to 0 energy. I can't get to 0 temperature. The lowest I can get to is this simplest possible case of a 1 hump wave function, half a sun wave. If I add energy to this electron, I can get 2 humps. I can have a wave function that looks like that. I can have more, 3, 4, do whatever I want. But I have to be at 0 at the 2 ends. I can't do this, because this is not 0. I have to be 0 at the 2 ends, no matter what I do, no matter how much energy I have, no matter what else I do. So I can have a fixed number of these waves in here. This may look familiar if your memory is really good back to week 1, I think, maybe week 2, where we had the Bohr atom, and I had the wiggles of the electron in the atom, and it had to match up, it has to line up. I can only have 1 wiggle or 2 wiggles or 3 wiggles, and those are the different energy levels in my atom, and this is what was responsible for all the different phenomena that we were talking about. This is what's actually happening quantum mechanically. This is why I have to match up the wiggles. It's not really because the electron is wiggling around. I told you at the time I was kind of lying to you. This is the real answer. It's almost the real answer. An atom doesn't have infinitely high walls. But if I'm close, if they're high enough that I'm close to the bottom, it'll look like this. So I can have the 1 hump, I can have the 2 humps, I can have the 3 humps, and those are my different energy levels. That's how that comes out of quantum mechanics. That's also why, with this probability, when I show the pictures of the atom, where the electrons are, and it's kind of a fuzzy ball, or it's a ball up here and a fuzzy ball up here, you can't pin it down, that's what's happening. That's what I'm really drawing there is this wave function, the probability distribution of the location of the electron in the atom. And if I shoot something at that atom, and I bounce off that electron. Now I know exactly where it is. And I can do that over and over again. And I can draw that map of these fuzzy atom pictures. But the electron isn't in that particular place. It's just smeared out overall until I do it. So that's how quantum mechanics that I avoided talking about at the beginning gives you that picture of atomic physics that we went on and talked about for another hour and a half ago.
I don't know why the Heisenberg's cat, what's the thing of something being there and not being there? at the
Right,
same
so that's Schrodinger's cat.
thing?
And I'll give you a hint. We have Schrodinger's cat here on the front, and then Schrodinger's cat dead on the back. What that's related to is, and we'll talk about it in a few minutes, but that's really just a description of I don't know where this thing really is. Okay? I don't know if it's in this case or that case. And that bothers you, that I can't know. And so Schrodinger's cat was a way to say, well, let's make this example as silly as possible, as impossible as possible, and say I've got this cat that's either alive or dead. How can I not know that? And the solution to it is because,
It is both.
well, that's what I said, it's both, but the cat really can't be both. You can't have a cat that's alive and dead. The cat is a cat, it's not a subatomic particle. That's too, the reason is that it's, when we measure this thing, is when it's forced to choose. The measurement is not, we're talking about the observation of it, right? You think of, if I'm watching the monkeys are going to behave differently, I'm influencing their behavior. That's not what we're talking about. It's not the human observation. It's not that a sentient being with intelligence makes it an observation and recognizes something in their head. That's not the act of observation. The act of observation is a physical thing. There's an interaction that forces it to do one thing or another. And that's where people go wrong. Including physicists of old. There was a branch of, it's really that human interaction with that. And that's what causes the observation. And that's what the cat picture is. That's what it really shows. Is that it's not that I see the cat, it's that the mechanism that caused the cat to die, that's what I don't know. And once that happens, it's constrained one way or the other.
And it has nothing to do with the idea that when you watch it now, it's in this place, and if you watch it 10 minutes after, it's in that place, and it's always circulating, or it's just like, it's at all times everywhere.
It's all times everywhere until you watch it. Once you watch it, then it's a regular particle. It just sits there. Quantum mechanics kind of goes away in that sense. Now, if I go away long enough and it's able to go back and do its thing,
Right, you
then it would be different. But it's not circulating. It's just smeared out all over the place. Let's see. Okay, so what this leads you to? So we have our well. That was a well with an infinite height. Now I'm going to draw something a little bit different. I have a well here. I have another well over here. But they're not infinitely high. They're high up here on the outsides. In the middle, they're not so high. I got two buckets. Now I can think of this as two bowls with a marble that I can put in either bowl. The two bowls are side by side. So I have my electron in here. I drop an electron into this well. Now if I drop a baseball into this well, and I go away, and I come back, the baseball is going to be here. If I drop an electron into this well, it's not in a particular place. It's got this wave function. And what we saw with an infinite well was the wave function looked like that. But if I have a barrier that's not infinitely high, the electron isn't like that. The electron wave function looks pretty much like that, and then like this. A little piece of the wave function is over here. There's nothing in here, but the wave function has a piece that's over there. The way the arithmetic works when I take the energy required to get over less than 0. This is not because the electron can jump over the wall. It doesn't have enough energy to get over the wall. It can only get this high. It cannot get over the wall in any conventional sense. It doesn't jump. It doesn't sometimes have enough energy to get over. It doesn't go through the wall. The wave function here, should use different, and the wave function in between is 0. There is no probability, 0 probability of finding it in the middle of the wall. It's either on one side, most likely. There's a small chance that it's on the other side. If I add more energy and it gets closer and closer to this grows as well. But what I have is the ability for an electron to magically jump over here. Is it jumping? I don't know if you say it's jumping. it's actually part here and part here. It's maybe 95% here and it's 5% here because it's just smeared, it's not anywhere. And if every 5 minutes I turn around and look, I'll see once in a while I'm going to catch it over here. Once in a while I'll catch it here. The wave function will collapse, it'll sit there. Once it's here, then it's there.